All right, guys, for 423, you'll notice we did not put any, I didn't put any practice on this. There's only one thing from this lesson that I think it's important for you to know. As a matter of fact, they've actually taken residuals out of the standards for ninth grade, but I do think it's an important concept, and it's pretty easy. So there is going to be a single question on the test on it. So we are going to go over it just a little bit. Make sure you watch this video because there's no practice on these. So residuals is similar, I guess, in a way to a mean absolute deviation, except you're not actually finding the mean or the distance from the mean. What you're doing is you're plotting points and you're drawing a line, and then you're seeing how well your line fits that set of data by finding how far above or below the points actually are that line, from that line. Okay, so if you look at here, look at this example. Here's your scatter plot of, here's the data. For example, 1 days, and then the height in centimeters. And if you notice, those dots are all, you can pretty easily see that that's a straight line, or pretty close to a straight line. So the line of best fit would be something like this. And if you notice, the dots aren't all exactly on the line. Some are just a little bit above and a little bit below. For example, here at 1, it's a little bit below. Here at 6, it's a little bit above. All right, so what you do if you calculate the residuals, you plug in the points into the equation and see if they, see what they would actually be. And again, we don't really want to round here. And then we're going to do the residuals, which means we're going to see how far away the actual points are from the predicted values. Again, you don't have to calculate any of this. You just need to be able to recognize a residual graph and explain what it means. So when we plot those residuals on a number line, what you get is this sort of up-down, kind of nonsense looking graph. And that's actually what you're trying to find. You want the graph to have no particular shape. If it does that, if it's truly scattered, that means that a linear function is the best fit for that data. So that's it. That's all you're looking for. Now, on the other side of things, we'll look at an example of what I mean when it doesn't work out that way. So Lindsay created a table below for the population of fruit flies over the last 10 weeks. And she estimates that the population of fruit flies can be represented by this equation down here, y equals 46x minus 40. Using the residuals, determine if her representation is a good estimate. So the first thing you're going to do is plug in 1 through 10 and get those values, and then they're going to add or subtract, subtract to compare to get those residuals. And what you find when she does her residuals is that this has a very definite, non-scattered shape. Again, we're not looking for it to be linear here when you plot residuals. We're looking for it to be scattered, truly scattered. In other words, it doesn't have any defining shape, where this obviously does. This, as you can see, the scatter plot has a sort of, again, I'm sorry, I'm doing this on my mouse and keyboard here, has a sort of U shape, right? It's not scattered like that previous one was. It was up, down, up, down, up, down, up, down. This one actually has a defined sort of shape. That doesn't mean it's a quadratic function or some other crazy kind of function that we hadn't talked about. All that tells you is because it's not truly scattered, that a linear function is not the best fit. Okay, so that's what you want to get out of that. It definitely has a U shape, and that indicates it is a non-linear estimation, would be a better fit. So this function that she had is not a good estimate of the data. That's all I need you to pick up from 4.2.3. Okay.